Good morning, year 12s, very nice to see you. I see that lots of you have got on well with what is on Seneca Learning, so thank you very much for doing that. There's one or two people that need to just finish that off, but that covers everything that we talked about alcohols. And today we're having a little look at the chemistry of haloalkanes. So we have looked at how to name them, so I'm not going to go into that depth. But we know that we have the prefixes chloro if it's a chlorine-containing compound, bromo if it's got bromine in it, iodo if it had iodine in it, and so on. And we would give the position where it is. So the first thing I would like you to do, though, is I would like you to draw a Boltzmann distribution and explain how an increased temperature gives an increased rate. So I know this is not something that we've done for a long time, but it is important that we review things regularly. I'm going to pause for a second just to let you do that. Okay, hopefully you have done that and you have a set of axes that look like this. Now, there is a little bit of flexibility, so over here we have our number of molecules. That could be said as number of particles with a particular amount of energy, or number of molecules with a particular amount of energy, and along the x-axis we have energy. If you have called it kinetic energy, that's absolutely fine. We should have on here two curves, so we should have, that's not so bad. We should have a curve that perhaps looks like this. The important things is that down here it starts at the origin, so mine is a little bit dodgy, but that is because I'm using my finger on an iPad, and that we have a peak somewhere, and then as we tail off at the other end, that we never touch the x-axis. If we said that that is our low temperature, then our high temperature one, because we can do it like this, should look something like that. The key point being that the peak is down and to the right. Everything has been broadened out. We do need one extra thing, and that is that we need to have labelled on our activation energy somewhere. Our original reaction, these particles that are highlighted would be the particles that would be able to react. The key point that we need to say is that we have all of these additional particles that now have energy over the activation energy and are therefore able to react. Don't forget, of course, that temperature is a little bit of a double whammy, so it means that we've got more frequent collisions as well as more of those collisions being successful. Okay, but those are the key features that we need to see. I would like you now, because we're looking at a mechanism again today. We have looked at electrophilic addition, we've looked at nucleophilic reactions. We've looked at free radical substitution. So today we need to know what a nucleophile and an electrophile are. Again, I will pause just a second for you to do that. Okay, hopefully you have defined a nucleophile as an electron pair donor. Now, that could be a lone pair, doesn't need to be a lone pair, it could be a negative charge. It doesn't matter. And then an electrophile is an electron pair acceptor. Okay, of course, nucleophile means that it loves positive charge, as we would see in the nucleus, and electrophile means that it loves negative charge, as we'd see with those electrons. Can you please, for me, draw one chlorobutane and include any relevant dipoles in that? Again, I will give you a little minute just to do that. Okay. Hopefully you have a molecule that looks something like that. Don't worry if yours doesn't zigzag like I have got mine. Mine is purely that way because it's attempting to show the tetrahedral shape around each of those carbons. Because of course each of those carbons has 4 bonding regions. Those will repel each other maximally, giving us 109.5 degrees around each of those bonds. But that's why it's showing that. We do have a relevant dipole though. We've got a delta minus and a delta plus. Let's get rid of that. Delta minus and a delta plus. So that's because, as we know, chlorine is a lot more electronegative than carbon. So that means that the electron density in that double bond has been withdrawn around the chlorine, making the chlorine partially negative and the carbon partially positive. Okay, that does, however, mean that we can actually do some chemistry to this. As we know, alkanes are very unreactive, they're a bit boring, but as soon as we end up with some other functional group, then our functional group is of interest. So here, that delta positive carbon means that we're open to nucleophilic attack. Examples of nucleophiles are the hydroxide ion, water molecules, ammonia molecules, and cyanide ions. Today we're mostly going to be looking at the hydroxide ion. Do notice how I have drawn this. If you're doing a mechanism, you need to either show your hydroxide with its 2 electrons over here, let's make them slightly bigger, and you can have your negative charge anywhere, or if you're not showing the pair of electrons, it's really important that your negative charge is on the oxygen atom, because that is actually where it is. Okay, so if we're drawing a mechanism, it's important that we draw it as one of these two options. Personally, I draw my hydroxide ions like that. Okay, but of course these are all nucleophiles, so those we can see either have a negative charge or a lone pair of electrons. That allows them, if we go back for a second, to be an electron pair donor. Okay, so if we have a look at the mechanism, you'll notice that I have used R up here, so I don't care what the rest of my molecule is fundamentally. If I have this carbon halogen bond, then I can do this nucleophilic substitution. It's a nucleophilic because we're using a nucleophile. In this case we're using hydroxide ion, and it is a substitution because we're going to be taking the place of the halogen. Okay, so as a generic thing, our halogen could be chlorine, bromine, or iodine. If we had multiple ones on our same molecule, then we could do nucleophilic substitution to each of those. Okay, now you'll have to bear with me because I am using my finger on an iPad, but our rules are still as they were. We need to use curly arrows, and we need to show our curly arrow going nicely from the negative charge to the atom that the electrons are moving to, so in this case the partially positive carbon. Okay. Once this has happened, if that was all that was going to happen, then our carbon would have 5 bonds, and that's not okay, so we have to break a bond, and the bond that we're going to break is the carbon halogen bond. This process is, as I said, called nucleophilic substitution, because we're using a nucleophile and we're substituting it, but more specifically than that, this is an example of hydrolysis. So hydro, talking about water, lysis, if we remember back to homolytic and heterolytic fission, is all about bonds being broken. So hydrolysis is using water to break a bond. Here we're using aqueous hydroxide ions, but it still counts as hydrolysis. We're fundamentally effectively using the water molecule itself. Okay. Now, that mechanism is really important. You need to know this mechanism. There is an alternative, and if you've got the black book, it does talk to you about the fact that there is an alternative, but we learn this mechanism. So for those of you that are interested and go and have a look, this is what we call as an SN2 reaction, so that means nucleophilic substitution, so S for substitution, N for nucleophilic, and then 2 because in the fundamental point of this, there are 2 molecules involved. There's our nucleophile and there's the molecule that we're attacking. This reaction can actually also happen in what we call an SN1 method, where first this breaks and then we end up with a carbocation. So we would end up with that, and we would have our X minus floating around somewhere. Now our hydroxide ion is able to attack in, like so, and we've got the same reaction. what I've done in red is SN, not SN, SN1. What we've got in blue is SN2. Fundamentally, you don't need to know that, you just need to know the blue mechanism. But if you're having a look online and you see other options, then that is our two options. And it's all dependent on how strong that carbon-halogen bond is. So, the carbon-halogen bond, they're not all the same strength. We can see that carbon-chlorine bonds are stronger than carbon-bromine bonds, are stronger than carbon-iodine bonds. For this reaction, other than the fact that we need to have some electrophilic, some electronegativity difference, it's not how electronegative and how polar the bond is that is important. What is important, crucially important, is how strong those bonds are. Because we actually find that all of these reactions happen at slightly different rates. Okay? Generally they're a bit slow at room temperature, so we'd normally heat them, but they all go at different rates. And what determines that is how strong the bond that we are breaking is. So, carbon-chlorine containing compounds, those will react the slowest. Carbon-bromine, somewhere in the middle. Carbon-iodine would be the fastest reaction because it's the easiest bond to break. Okay, so that's really important. Don't think at this point, other than the fact that we needed that electronegativity to get that permanent dipole, I don't care about that beyond producing that dipole. Okay, and the strength of these is not so much dependent on the electronegativity, it's more the size of the atoms. Okay, so determining which haloalkane we would have is a arguably slightly awkward situation. You will not be able to tell by looking at them. They will all pretty much be just clear colourless liquids. So if we imagined on this slide that my test tubes are full of one bromobutane, one chlorobutane and one iodobutane, just by looking at them we don't know. Okay, so what we do is we add some aqueous silver nitrate. Silver nitrate will react with any halide ions that are present. Now obviously if we had one bromobutane, there are no halide ions present as yet. But aqueous silver nitrate, as it is aqueous, that tells us that there's a large quantity of water in there. That water can react as a nucleophile, doing this hydrolysis reaction. Okay, it will be quite slow, and we do have the complication that our haloalkanes are pretty non-polar. They're not going to dissolve in water well, but we need them mixed with water for that reaction to happen. So we're going to add a solvent, and we're going to add ethanol. Yeah, because as we saw, ethanol has its non-polar tail. It's not a very long one, but it does have some non-polarity to it, as it has a polar end as well, and it can create hydrogen bonds with water. So it will dissolve well in water, and it will dissolve fairly well in our haloalkanes, which means that we can use it as a solvent to bring those water molecules into to be able to actually react with the haloalkane. We don't need a lot of ethanol, but we're just needing enough to make sure that it actually mixes. Now, on the right, these are the products. So I know from looking at this that this was my chlorine containing one. I know this because, despite the fact that it looks exactly like the test tube on the left, we have a white precipitate. Okay, so in all of these we're producing a precipitate. In this case it's white. That tells me that it is silver chloride that has formed. Here it's bromine or bromide ions that were present at the end of our reaction, because of course remember that our reaction produces halide ions, not halogens, but it produces halide ions, and we've got a cream precipitate. And then as our last one, this is because we've got iodide ions present and we've made a yellow precipitate. Sometimes, if you were to do this practically, it's difficult to tell whether your precipitates are white, cream or yellow, unless you've got all three with you. Okay, so generally, though, they will tell you what the result is, because practically it can be a little bit challenging to work out what it was. We also need to know what is going on with silver nitrate. So silver nitrate, fundamentally, the bit that we're interested in is the silver ions. Silver ions will react with halide ions, and they will form silver halides. Those silver halides are solids versus our aqueous ions over here. This gives us our test. Now, the colours are one way that we can tell the difference, but we can also tell which one's which dependent on how quickly they go. Remember, we said that the carbon-chlorine bond is the strongest, then the carbon-bromine, then the carbon-iodine bond. So, that means that this one will be the fastest, and this one will be the slowest, with the bromoalkane somewhere in the middle. We could get a feel for that practically by timing how long it takes from the addition of the aqueous silver nitrate until we cannot see through our test tube, in a similar way that you used the hydrochloric acid and sodium thiosulfate experiment in year 11 with a cross at the bottom. But we can practically do that. Hopefully that has been helpful, and I will, I think, probably do another video for you guys for our next lesson as well.